you very much. So today we are going to give the second lecture about parameterized algorithm and parameterized techniques. But before I start with the material for today's lecture, I need to make some clarification / errata for lecture 1. So when I was presenting the last time this LP guided branching algorithm for the vertex cover problem, at the very beginning I said let's do some sanity check that the problem is polynomial time solvable for k equal to 0, for the gap being equal to 0, and I tried to persuade you to believe me that the following problem can be solved in polynomial time. So I'm given some LP, yes, and the question is there, say, variables? In our case, variables were belonging to the interval 0, 1. And the question is there an integral solution? Of optimum integral solution of value equal to the optimum of the relaxation. Yeah, so can you make an optimum fractional solution that is actually also integral? And my argument was, okay, let's try to force some variable to 0 and see if the value of the LP bumps up. If not, then I can fix it. If it bumps up, I can try to fix it to 1 and see if it goes up. If not, then I can fix it. Otherwise, I do not have an integer solution. And this is, of course, wrong. In general, because, well, it can be that forcing a variable to 0 doesn't go the fractional solution to go up. However, there's actually no integral solution with the value there is 0 there, but maybe there is one with 1. So this in general argument is wrong. In our case, it was correct because we knew that we have persistence. So this argument works if there is persistence. So recall that persistence was this condition about an LP, that if the LP is able to set a variable to 0, say, or 1 in an optimum fractional solution, then when solving the integer variant, I can safely put a 0 or 1 there, and I do not lose on the optimization. So in presence of persistence, this kind of strategy works, and indeed in polynomial time, in general, this. Yeah, because, well, in general, it is like that an solver for the relaxation will just give you some fractional solution on the facet of this polytope with optimum fractional solutions, and now you just ask, is there a integer vertex of this facet? And in general, this can be hard, and those problems like finding the best, like finding a solution above a lower bound above the LP. Sorry, something's wrong.
The sound is going up and down.
Ah, okay. What should I do? Okay, I will keep talking. Okay.
Now it's not working at all.
All right. I think now it's working. Can someone nod, please, if they can hear me?
Yes.
We did just test it for like half an hour and it did work, so I don't know what's happened.
Let's let Michal keep trying.
I'm trying. Is it working now? At all? Yes, there is some yes. Could we get more yes?
Yes.
Good. Okay, so it's working now. We'll see whether this persists. We're talking about persistence. Good. Good. So just a quick recap for those of you who haven't heard what I was talking about. So I was trying to convey the last time the following argument that given an LP with variables in the range 0, 1, I can check whether there is an integral solution of value equal to the optimum value of the relaxation by iteratively using self-reduction, trying to force a variable to 0 or to 1. And if this doesn't bump the LP, then I can fix the variable. So in general, the strategy does not work. It works under the assumption that the LP we are working with has this persistence property that I later on proved about the particular LP for vertex cover we were talking about. So thanks to Fritz for catching this. I wanted to clarify that. Okay. Yeah, the volume is not good. Okay. Then you have that the volume is highly dependent on direction you speak towards. This might be true. Okay, but this was even worse, yes? What about now? Loud and looks at the black or felt when looking to the audience. So I need to okay, sorry guys, I will just need like that. Okay, but now it's working.
But can you try to put the headphone on? Yeah.
What now?
Yeah. Yeah.
Now it's better?
Yes.
Yay! Okay, because last time it actually did not work at all. Okay.
Okay.
Good. Okay, going back to the persistence. So in general, when you are working with a parameterized problem, you can always make some LP relaxation, and you can always think about the problem, some problem parameterized by the gap between the optimum solution and the value of the relaxation. Yeah. So in our case, we have proved that for vertex cover, this gives you a fixed parameter tractable problem. But in general, this problem can be hard even for the gap being equal to 0. Yeah, this is exactly NP hardness of this. So let me give you a very small example showing how this can happen. And the example will be for free hitting set. Yes, so you've got a universe. In this universe, you've got a bunch of hyper edges of degree consisting of 1 or 2 or 3 elements, and you want to hit all those sets by picking k vertices in your universe. Yeah, so here I would pick this guy probably and hit all of those 4. Probably this guy. I need to still hit this guy, so maybe this would be a solution. Yeah. So I claim that this is NP hard already for k minus LP equal to 0. So already checking whether there is an integral solution of value equal to the optimum of the natural relaxation is already NP hard. Yeah. So a quick so this will be a very simple reduction from free set. Yes, to this problem. So a free hitting set with k minus LP equal to 0. What I do for every variable, I create 2 elements of the universe, call them x and not x. And I put sets like that. So I create hyperedges of size 2 for each element of the set consisting of the variable and its negation. And then for every clause, I simply put this clause as hyperedge. Yeah. So then I need to pick one vertex from each, yes, in order to hit all the clauses. Right? So then FreeSat is equivalent to finding a solution of size k, here, or size n here, yes, where n is the number of variables. But you see that every LP, every fractional solution needs to pick at least n here, because, well, you have n disjoint hyperedges. Yes? And actually, there is an optimum LP solution of weight n by putting half on each variable. Yeah. So here, LP is equal to n, and asking whether the integer solution has value, the optimal integer solution has value n is already NP hard. Yeah. It actually shows a little bit more. It actually shows that this is even NP hard for the gap between the optimum solution and the packing number. Yes, so the integer solution to the dual. Yeah, because here we've got a packing constraint. Good. Okay, so this was just a clarification that really we need this kind of persistence property, strong properties about the ILP in order to make this LP guided branching work. Good. Okay, so this was clarification from the previous lecture, and we now can delve into further techniques and avenues of parameterized complexity. And the first notion I want to speak about today is kernelization. So during the previous lecture, we have seen that in many problems we devise some first simplification rules. Yes, that you remove vertices of degree 0 and degree 1 and degree 2, the instance gets simplified, and so on and so on. So kernelization is, the idea is to try to take this this concept of simplifying the instance, in pre-processing the instance in polynomial time, and turn it into a robust complexity theoretical framework for studying pre-processing routines. Yeah. So what is a kernelization algorithm? So if I have some parameterized problem, say call it I don't know, Q. Q is a parameterized problem. Then a kernelization algorithm is an algorithm that takes an instance of the problem, and imagine that this instance is huge, but has a small parameter. Yes, does some polynomial time preprocessing to it, and outputs another instance. Okay, call it I prime k prime, that hopefully is small, in the sense that it preprocesses it in polynomial time in order to carve out parts of the instance that should be easily resolvable. Yes, so in polynomial time we transform it into a new instance that hopefully is small. So now what are the conditions? The condition is that this instance, the size of this instance, should be bounded by a function of this parameter only. Yes, so the condition is that the size of I prime and also the size of the output parameter is bounded by some function of the input parameter. Yeah. So essentially, the idea of a kernelization algorithm is that if we are dealing with an NP-hard problem, probably we cannot solve it in polynomial time, but at least in polynomial time, we can compress it to a kernel which is of size bounded by the parameter only. Yes, so to carve out all the parts of the instance that are really not necessary, yeah, or easily resolvable. So let's see some example to make this thing more concrete. And for the example, of course, we will take vertex cover. Yeah. So a typical kernelization algorithm is usually based on the so-called reduction rules. So if you see some possibility of reducing the instance, you just apply it, and the argument is that if you apply it exhaustively, you get a reduced instance that hopefully is small. So reduction rule 0 would be to delete isolated vertices. Yeah, this we have already seen that works. We actually could even resolve vertices of degree 1 and of degree 2. I will actually not use it here. So reduction 1, sorry, would be the following, and this is the key reduction. What happens if I see a vertex U with degree larger than k? Well, I've got a vertex U. I know that I'm looking for a vertex cover of size at most k. And here I have more than k neighbors. Then I'd better take this guy to the vertex cover, because otherwise I would need to have more than k vertices there. Yeah, so I can greedily take this guy to the vertex cover. So then I can remove U and decrease k. Yeah, so this is another simplification that I can do. And finally, reduction 2 is that if I applied this reduction and this reduction exhaustively, yes, so I always assume that I just try to apply the lowest rule possible, then if I have more than k-square edges, then I can safely say no, in the sense that I do not have a vertex cover of size k. Why? Because if rule number 1 is not applicable, then every vertex can cover at most k edges. So by just counting, I will not cover all the edges if there are more than k-square of them. Yeah. So observe that in this kernelization, actually I allowed also for the kernelization algorithm to actually solve the instance, and this is typical that you have this assumption as well, and reasonable, I guess. Yeah. So this means that this algorithm that iteratively, exhaustively applies those rules, yes, if it did not resolve the instance by rule number 2, I end up with an instance with at most k-square vertices. And if there are at most k-square vertices and there are no isolated vertices, this also means that there are at most 2 k-square edges. Yeah. So the instance is now bounded by a polynomial in the size in the parameter, actually here k-square. Okay, so this was one example of a kernelization for vertex cover, but actually we have also seen kernelization for vertex cover already during the previous lecture. So example 2, because on the previous lecture, we have shown a preprocessing based on linear programming that reduces the instance to an instance where all 1/2 is the only optimum fractional solution. Yeah. How we did it, we proved the half integrality and persistence, and we showed that if we are able to find a solution with 0 or 1 half integral, then we can greedily take this choice. Otherwise, this is the only half integral solution. But then, if all 1/2 is the only fractional solution, then what I have that n, the total number of vertices, half. Yes, this is the value of the solution, must be smaller or equal than k, my parameter, because otherwise I can immediately say no. Right? Because this is the value of optimum relaxation. Yeah, so I'd better have my parameter, my budget for integer solution larger. Yeah. So this means that I have n at most 2k. So this is now, after applying this rule, I got the kernel with at most 2k vertices. Yeah. Note that the number of edges can be still quadratic in the number of in k, and this is actually necessary in the sense that there are information theoretic arguments that under certain complexity theoretic assumptions, you cannot get a kernel of bit size better than quadratic. Here. Okay, so this is basic setting of kernelization, and kernelization was really a flourishing field of parameterized complexity, let's say 5-10 years ago. There are many kernels for different problems. We usually care about polynomial kernels, so kernels where the size of the output is polynomial, because there is a simple argument, maybe I will not go into this, that existence of any kernel with any function f on the size of the kernel is actually equivalent to the problem being fixed parameter tractable. So getting exponential kernels is not really that interesting. However, getting polynomial kernels is actually interesting, and there is usually quite a number of nice graph theory involved in this kind of arguments. So maybe to give some examples and non-examples, where can you expect polynomial kernels? So for examples, we already have seen vertex cover, which has a kernel with order of k vertices and k square edges. Yes, you can, yes? Yes. Yes. So yeah, I've got at most k square edges, of course, and therefore at most 2k square vertices. Yeah, thank you. I was too quick. Good, but yeah, here I have shown a kernel for vertex cover with 2k vertices and quadratic number of edges at most. Yes, you can generalize this idea, in particular this idea there, to deheating set. So vertex cover is like a 2-heating set, right? Because I have a hyperedges of size 2 that I need to hit with k vertices, and here we had the deheating set for larger values of d. For deheating set, the size is order of k to the d, and again, as far as I remember, there's an information theoretic lower bound that you cannot get bit size better. I am now unsure. I think that there are papers saying that you can actually get like k to d minus 1 elements in the universe, similar as here. So the number of vertices is 1 degree smaller, but take this with a grain of salt. I did not check it. So yeah, there is a number of results in this vein. For example, for feedback vertex set problem that we have seen during the last lecture, there is a nice kernel with order of k square vertices. And this is due to Stefan Thomaset. And there's very nice graph theory involved in this. I really recommend this result. So here were some examples, maybe a non-example. A non-example would be k-path. K-path. So the problem is that we are given a graph G and an integer k, and the question is there a simple path on k vertices? Yeah. So here I've got the graph, and I need to find a path on k vertices that doesn't have self-intersections. Yeah, this will be a path on 7 vertices. Yeah. So of course, if I put k equal to n, I've got Hamiltonian path. So this problem is NP-hard, but I can parameterize it by the length of the path. And this is a very well-studied parameterized problem. And in particular, it doesn't have a polynomial kernel. So the theorem, and here is a little bit, I'm a hesitant whom to attribute it to, but let me attribute it to everybody. So there was one paper of Bodlander et al. Who actually proved this theorem as like that. And there was another paper by Fortno and Santanam. Yeah, that says that k-path has no polykernel. So kernel with polynomial guarantee on the output size, unless co-NP is contained in NP with polynomial advice. Yeah, so this is some complexity theoretic assumption that we need here. So the story was that Fortno and Santanam proved some complexity theoretical backbone theorem behind this theorem, and then Bodander and others applied it to the setting of kernelization and got this result. Yeah. So I will not prove this theorem, though the proof is really elegant. I will just give you an intuition why this is the case. So imagine that somebody gave you a lot of instances of K-path. Imagine, first of all, assume that there is a polynomial kernel for the K-path problem. Yeah? So imagine that somebody gave you a lot of instances of K-path, say n much larger than k, and all of the same, all with the same parameter k. Yeah? So these are just graphs. So now let me combine all of those instances into one instance by just taking this joint union. Yeah. So I just put those graphs next to each other. I take the disjoint union of those instances and observe that this instance has a k-path if and only if at least one of those had. Yeah. So this is something that we call an OR composition. That sort of takes an unbounded number of instances and merges it into one instance that behaves like an OR at this junction of the input. So what would happen if I now had a polynomial kernel? I could apply it to this combined instance and reduce it to something very small of size much polynomial in k, which is smaller than n. So in a sense, by an algorithm that runs in polynomial time, I could take very many instances of an NP-hard problem and compress it to bit size that is much smaller than even the number of those instances. Yeah. So something is fishy here. I should have resolved some of those instances on the way, but they're NP-hard. Yeah. So this is the complexity theoretical intuition, and you can formalize it under this assumption. Okay, so kernelization is nice because there is a lot of graph theory involved, elegant graph theory. You can do it for many problems. For many problems, you cannot do it. And you have also a nice methodology for proving lower bounds against kernelization. So this is essentially everything I wanted to say about kernelization. Kernelization will come back at the end of this lecture, hopefully. Yes? There's a question. Both of them imply FPT. So of course, if I've got a problem that has a kernel, then it is fixed parameter tractable under assumption that it is decidable, because I can compute the kernel and then brute force the kernel using any algorithm for the problem. Yeah. However, if you are FPT, if your favorite problem is FPT, then there is a easy argument that actually it has some kernel, and the argument goes like that. Imagine you got an instance, yes, and imagine that the size of the instance n, yes, is larger than f of k. This f is you've got an algorithm working in time f of k times n to the c. If the size of the instance is larger than f of k, then actually you can solve it in this running time, which is bounded by n power c plus 1, which is polynomial, right? On the other hand, you've got n smaller or equal than f of k, and you've got a kernel. So this is a stupid argument that shows that if I have an FPT algorithm, by just juggling with it, I can compute some kernel. Yeah. So here in this argument, if you look at the details, I assume that f of k is efficiently computable, but you can make this argument also work without efficient computability of f. Yes. Yeah. Yeah. Oh, of course. Meaning k-path has an exponential kernel because k-path is fixed parameter tractable. We will see this within the next 10 minutes. Yeah, so k-path has an exponential kernel but doesn't have a polynomial kernel unless stuff happens. Sorry? we are mostly concerned about curiosity, like getting smaller is better. You can motivate kernelization from many different different perspectives, like compression, this kind of stuff. I think that we are particularly concerned about polynomial because we have this toolbox, and we really see a conceptual difference between exponential size kernels and polynomial size kernels. Yes, it seems that really this ability of encoding at this junction of instances really differentiates the two in some sense. No. Meaning, if you have a polynomial kernel and you've got a sort of say a single exponential brute force algorithm, then you've got like a 2 to the power poly k FPT algorithm. Yeah. So you can view also kernelization as sort of a way of getting FPT algorithm, because you can do kernelization and then brute force the kernel. But usually you do not get the most efficient algorithm. Yeah. Good. Sorry. Yes. So the question was why do we care about polynomials, polynomial kernels, compared to exponential kernels, and does it impact the efficiency of FPT algorithms that we get from them? Good. Am I actually, can you listen like that? Because this is much more convenient for me, because this headphones having them completely on is really awkward. Everything is okay now, right? Okay, good. Yeah, there's at least one, yeah. Good. Yeah, nobody complains. So let me continue like that. Good. So this was about kernelization, and then this is just for reference, because this is a big part of parameterized complexity, though it doesn't have that much to do with combinatorial optimization in my opinion. So now another technique in parameterized complexity, and a technique that is very important, and you can apply it in many different settings, namely color coding. And this is a technique that is really magic once you see it the first time. So how this works? So I will now show you an algorithm, FPT algorithm for the K-path problem. Yeah, so the problem of finding detecting if there is a simple path in a graph with K vertices. So let me change the problem a little bit and discuss a problem I will call rainbow K-path. I will work with directed K-path, so in directed graphs, the technique will work in directed graphs the same way. So why not a larger generality? So in the rainbow K-path, I'm given a graph G, but I also get a coloring, call it, I don't know, C, that colors the vertices of a graph with colors from 1 up to K. So that's input. And the question is whether there is there a rainbow K-path? So a K-path that looks like that, say here is color number 1, here is color number 2, here is color number K. Maybe I'll actually draw those intermediate colors. And I want my K-path to have the first vertex of color 1, the second vertex of color 2, the third vertex of color 3, and so on and so on. So I want a K-path that is properly colored, in the sense that the if vertex is of color E. Yeah. So this coloring in the given at the beginning describes me which vertices are allowed for which element of the K-path. Yeah. So I claim that this problem is actually polynomial time solvable. Yes. Yes. The first must be the first, the second must be the second, and so on and so on. So it is really colored like that. The order of the colors matters. Yes. We will actually think about the second variant in a minute. So the claim is that this problem, so rainbow k-path, is p-time solvable. Why? Because I can make a very simple dynamic programming for this. Yes. So dynamic programming, yes, will just for every consecutive vertex in the graph, say of color I, say here is vertex U. In the dynamic programming, I will check whether there exists a prefix of a path that uses the previous colors. Yeah. So then the dynamic programming at vertex U will be just the disjunction over all the V that are predecessors in the previous layer has color I-1, yes, of dp of V. Yeah. So this is basic dynamic programming. I'll just go left to right. Okay, so how to reduce general k-path to this rainbow k-path? And the trick is that we will just pick the coloring at random. So what I will do, I will take the vertex set and I will draw at random a coloring of this vertex set with k colors and try to check whether there's a rainbow k-path. Yeah. So the algorithm first draw a random coloring C of the vertices with numbers 1 up to k. Yes. And second, check if there is a rainbow k-path. Okay, so this is a polynomial time algorithm. It is randomized, yes, but it solves our problem. Well, it has a chance of finding a k-path in the graph. Yes. So what is the probability that it actually finds a k-path, assuming there is one? So assume there exists a k-path. So the answer is yes. What is the probability of success in the sense of actually detecting a k-path by this algorithm? Well, the algorithm will definitely detect the k-path if the k-path will be colored, if the solution will be colored by our random coloring 1, 2, 3, and so on, like in a rainbow way. Yeah. So what is the probability of this happening? Each of the k vertices of the k-path must be colored with the right color. So this is 1 over k to k. Yeah, by drawing a random, I mean uniformly at random. Yeah, so every vertex independently gets every color with the same probability. Yeah, 1 over k. Yeah, so the probability of success of finding a k-path is 1 over k to k. Yeah. So then what I will just do, I will repeat k to k times this polynomial time algorithm. Yeah. So then what is the probability of failure of detecting a k-path? Yes. Well, it is bounded by the probability that I fail to detect a k-path in every iteration is the complement of this 1 over k to k. And then I do it k to k iterations. I try it. So this is bounded by 1 over e. Yes, which is bounded by 1 over 2. Yeah. So now the running time of this algorithm is, well, we did some polynomial time subroutine, this subroutine here, and we just repeated k to k times. So this is FPT. Yeah. So this is a very magic trick once you see it at the beginning, but it works in surprisingly many different settings like that. Yes? Yes, you can de-randomize it. We will see it in 15 minutes, I guess. Yeah. I'm not sure. Yes? But can you repeat to me actually? Yes, indeed, this would work. So the idea here of DeepSy is to take a random permutation of the vertices, yes, and then orient the edges, keep only the edges that go further in the permutation. Then you get a DAG, and in a DAG it is easy to make a DP as well. And the probability that a permutation on the K path is being permuted the right way is 1 over K factorial. Yes. So in this way you can improve this K to K factorial. Yeah, nice. I did not know this trick. Yeah. Good. This will be in 5 minutes. You're really jumping ahead, guys, today. Good. But very good, very good, very good. Yeah, so observe that this is a randomized algorithm. Yes, this is a randomized one-sided error. If there is no K path, then definitely I will not detect one. Yes, but if there is a K path, I have probability half, yes, at least half of actually finding one. Yeah, it can be the randomized. We will talk about it in a minute. But now let's improve it to something like 2 to the order K. Yes, because this is like 2 to the order K log K. So the idea is to use the variant that was already mentioned here. So the variant where I do not insist on the colors being exactly 1, 2, 3 up to K, but I just want to have my path colorful. So a colorful K path input is again a graph together with a coloring of vertices, 2 numbers from 1 up to K. And the question is there a colorful K path? So a K path that is injectively colored. Yes, every color appears exactly once, but not necessarily in this order. Yeah. Okay, so this problem I think is already anti-hard, but we can solve it in time 2 to the K times polynomial in N using DP dynamic programming on subsets of colors. So how now this looks, we have those colors somewhere there in the graph, 1, 2, 3, up to K. And the question is whether there is a K path. So now my dynamic programming state, if I am at vertex U, and I assume that I have already used some set of colors X, yes, is there a K path that uses exactly those colors and finishes at U? Yeah, so the dynamic programming of U and X, where this is a subset of colors, is there a size of X path finishing at U, and using colors in X. Yeah. So this is like a, say, TSP-like dynamic programming. Yes. So if I want to compute, say, this state, Ux, what I will do, I will just make a disjunction over all the possible predecessors of dp of v and x minus the color of x, color of u. Yeah. So in this way, I will just collect more and more colors and keep track of which colors we already used. Yeah. The number of states of this dynamic programming is well, 2 to the k, because there are that many subsets of colors. So I got this running time of running the whole dynamic programming. Yeah. So we can solve this problem in running time 2 to the k times poly n. But now the idea is that if we do the same trick with random coloring, then we get a better probability of error. Yeah. Because now if I draw at random a coloring with numbers 1 up to k, the probability of success, now success is that my k path is being colored injectively. So now the probability of success is like the number of colorings is still k to the power k, but the number of good colorings is k factorial. Yeah. which is now by Stirling approximation roughly e power k, e power minus k. Yeah. So now, even though my subroutine works in exponential time, I can only repeat it e power k times. So if I do it like that, I get running time 2 e power k times poly n. Yeah, which is, I don't know, it's probably a bit below 5, right? Above, yeah, above 6 definitely. Good. So this is a color coding for kpath. Actually, for kpath, we know better algorithm. So I think for the directed one, and this uses algebraic toolbox that I will not be speaking about during this course. For directed one, we know 2k power times poly n. For the undirected, we know something even better. I think 1.62. I hope so. Definitely below 1.66. Maybe I'll just write 1.66 to be on the safe side. Poly n. But this too I am certain, because improving upon this is a big open problem. Good. So this was kpath. How much time do I have? Okay, 15 minutes. Sorry? Yeah, because well, we started a little bit. Yeah. Good. So this was color coding for the particular kpath problem, and conceptually, what happened in this color coding? Conceptually, kpath is a problem about disjointness. I want to find a walk on k vertices in a graph, but I cannot repeat vertices. Yes, and this is a constraint. This disjointness constraint, that this non-repetition constraint, is really what makes the problem hard. So what we did using kpath is sort of, we enforced this this constraint by just hashing the elements into different universes. Because if the elements are taken from different universes, definitely they are different. Yeah. So this is roughly what happens in all the applications of kpath, that whenever you want something not to be repeated, you can just randomly hash it into different universes, and therefore your constraints become trivial. So let me show you one more example of an application of kpath that will also be maybe closer to combinatorial optimization in some sense. I will call this problem, I'm not sure how to call this problem, but I will call it small expanding set. And the situation is like that. So the input is a graph G together with two integers, k and l. And the question is there a subset of vertices x of size exactly k, and at most L edges between x and the complement of x. Yeah, so the picture looks like that. Here is your graph. Yes, and I want to find a subset of vertices with a fixed size that expands only slightly, in the sense that here I've got k vertices, and only at most L edges are going outside of it. Yeah. So I want to give you now an FPT algorithm parameterized by k and l. So I now think that both k and l are small. So in particular, if k is small, then the set is small, but also the neighborhood of the set should be small, because, well, there are at most L edges going out. Yeah. So the neighborhood n of x should be also of size at most L. So what will be my algorithm? So again, I will randomly color my my vertex set. So randomly color the vertex set into, now I will use two colors using this color scheme, into blue and, well, let's call it red. I hope that it is red enough. Maybe orange. Anyway, let's call it red. And the good event Yeah. So in the previous algorithm, the good event, the event that allows us to find a solution, was the event that the k-path is being colored appropriately. Yeah. Either in a rainbow way or in a colorful way. So now the good event, I will say that the event is good if X, my solution, becomes red, is entirely red, and the neighborhood of X is entirely blue. Yeah. So I want to fix a coloring, and I want the situation to look exactly like that. Every vertex now gets a color, and I want that a good event would be that my solution is highlighted as red, and the neighborhood of my solution is highlighted as blue. Yeah. So what is the probability of the good event? Well, it is at least 2 power minus k plus L, because each of those k plus L vertices must be colored there. Here by randomly color, I just flip a coin, independent coin for every vertex. No, unbiased coin. Good, so the probability is good. It is bounded inverse in the parameters. Yeah. So how now assuming the good event, so assuming the good event, how can I find the solution? And I claim that, assuming the good event, that this is just knapsack. Why? Because now if I look at the graph, I've got some red connected components. So I'm looking at the connected components of the subgraph induced by the red vertices, and I've got the other part is probably somewhere blue. Yeah, and every red connected component needs to be taken to my set X entirely or completely disjointly. Yeah, because if to my solution X I take only half of this component, then actually there will be somebody red that will have neighbor also red. Yes, so every red component either goes entirely into the solution or is entirely gone from the solution. And also, whenever I'm taking to my set X a connected component, it brings with itself a certain number of edges. So now the components are items of my knapsack. The weight of the item is the number of vertices, and I need to get total weight k. Yes, and I'm optimizing the total number of edges outgoing out of it. Yeah, so this is now knapsack that I can solve in polynomial time. Good. So this is another application that reduces where color coding reduces an NP-hard problem to a problem that is polynomial time solvable by knapsack. Good. So this was this. Let me just say that actually this was the edge version of this problem, but the vertex version of the problem, where you want just the neighborhood to be of size at most L, not the number of edges, yes, it's actually W1 hard. So the vertex version is W1 hard, parameterized by K and L. And the reason is that this reduction to knapsack doesn't work because the components can share vertices. Yes, maybe here is a vertex that is neighboring both here, and it will be counted once. The idea is that those edges are being like independent between different components. Yep. And this makes the problem in the vertex variant actually already hard. Good. So this was color coding, and there was already a very good question about the possibility of de-randomizing this argument. And indeed, there are robust tools for the randomization. So robust tool for the randomization, they are called, oh, wipe it. I'm actually not entirely sure how they are properly called in the respective community of pseudo-random objects. I will call them splitters, as we do in parameterized complexity, but I've heard that actually this is not the good name. But anyway, a splitter is the following object. So actually, I will write the theorem. Yes. So suppose I've got some number, like I'm given n and k, these are parameters. N is the universe size, k is the number of colors I want to have. Yes. Then there is a family, call it f, of functions from this universe n, yeah, so numbers from 1 up to n, yeah, into k, so numbers from 1 up to k. Yeah, so this is a coloring of numbers from 1 up to n versus of my graph with colors from 1 up to k. Yes, with the following property, such that first of all, the family is small. I will write in a moment how large it is. And the second, for every subset of the universe, maybe call it A, of the universe, yes, of size k, there exists a coloring f in my family that is injective on A. Yeah, because in this color coding, what I really cared about is that for every subset of k vertices, candidates for vertices of my k path, there should be a experiment where these vertices are color distinctly. Yeah. So if I have a family with this kind of property, that whatever subset of the universe I take in my family called splitter, I will find a function that colors it distinctly, then I will just need to iterate through this family of functions and just check each of them one by one, yeah, instead of drawing at random. So the size of the family is, I think, e power k. This is what you expect from the probability of the good event. And for the pseudo randomness, you need, I think, to pay a quasi-polynomial factor and log n. Yeah, and you can efficiently compute it. Yeah. Yeah. This is k-wise independent hash family. So yes, so you just generate this family, and instead of drawing at random k to k times, e power k times a random coloring, you just iterate through all of those. Yes. So you pay with additional pseudo polynomial factor, and you pay with additional log n factor, which for a static algorithm is usually not a problem. But if you are working with different paradigms, sometimes this log n is problematic. For instance, if there was a recent work on dynamic data structures for a k-path problem, and then if you want to de-randomize those data structures, suddenly you would like to have like log n parallel copies of the data structure maintained, and this gives you additional log n in the running time of the update. Yeah, so sometimes this log n is problematic. Yeah. Okay, so this is a basic splitter setting. There are also analogous pseudo-random objects for coloring with two colors and so on. Maybe I will not go through all of them, but essentially for all kind of these random colorings, there are pseudo-random objects using which, in this way, you can de-randomize the algorithm. Just wanted to say that in this small expanding set example, I put the probability of being red and blue to be 1/2. But depending on the balance between k and l, maybe some other bias would be better. Actually getting something like putting k over k plus l and l over k plus l is the optimum, and this gives you a slightly better running time than this 2 power k plus l. Yeah, in case k and l are unbalanced. Just wanted to make sure that this is said, and also there are also pseudo-random objects for this lopsided random experiments. Good. Okay, so maybe in the I will take 10 more minutes to say something more about the last problem I wanted to talk about today, the last technique, and the technique that we actually have already seen today, namely dynamic programming on subsets. So once you think about it, dynamic programming on subsets is also an inherently parameterized technique, because usually if your universe over which you do dynamic programming on subsets is small, for example, the number of colors, then your DP works in say 2 power k time. So a typical example of this, and this is an example that I guess that most of you have already seen, is the Steiner tree problem. So you are given a graph. In your graph, you have a bunch of terminals. The graph may be edge weighted. This will not be a problem for the algorithm. You've got a bunch of terminals, T, call them, and you want to find the shortest tree that connects all the terminals. Yeah, so the tree S, shortest tree, connecting all terminals. Good. So my goal now is to prove a theorem, a result that is usually attributed to Dreyfus and Wagner from 70s, I think, that this problem can be solved in time 3 to the number of terminals times polynomial in the input space. Yeah. So observe that this is also a typical FPT running time. Yeah. Now the number of terminals is the parameter, and this happens a lot in this network design problems where you want to connect some set of things or disconnect some set of things. If the set is small, you can do dynamic programming on the subsets of it, and this is an inherently parameterized setting. Then, yeah. So how this can be done? This is a basic dynamic programming where essentially you think that you will build this tree from bottom up, and every time keeping track of which terminals you already connected. Yeah. So the dynamic programming state for a set of terminals, for a subset of terminals X, yeah, and a vertex U. The value of the state will be just the minimum length of a tree, the minimum length of a tree connecting T and this vertex U. Yeah, so U is a vertex of the graph. Yeah, so the situation is like that you've got this graph, you've got a number of terminals around. Yes, but so far in the state, you only care about some subset of them, say this guy, and this guy, and you've got some vertex, and you want to ask what is the cost of connecting all of those to this vertex here. So how then to make transition in this? So note that the number of states is roughly to the power number of terminals, yeah, times n. So how do you make a transition in this dynamic programming? If you want to compute the value of this state, you need to imagine how the tree connecting those terminals from X can look like. Yeah, here are the terminals from X. Here is my vertex U, and this tree probably goes a little bit from U and then branches into 2 subtrees, one connecting some subset of terminals and second connecting some other subset of terminals. Yeah. So if I want to compute this, I can make a disjunction sort of, or minimum over all possible disbranching points and over all possible ways this set X is being partitioned into left and right. Yeah. So this will be minimum over all the vertices V, yes, and minimum over all the non-trivial partitions of X or of X into Y and Z of I need to take the distance from U to V plus the how costly it is to connect Y to V and how costly it is to connect Z to V. Yeah. So dp of V and Y plus the dp of V and Z. Yeah. It can be that U is equal to V. Yeah, it can be that U is equal to V, then the distance is 0. Sorry? Again? There will be some point when they diverge, unless you are actually in the base case where X has no non-trivial partition, it is already one terminal. So the base case is the dp of U and one terminal is just the length of the shortest path. Yeah. So that's basic dynamic programming. So it has that many states, but I promised you 3 here. And the reason is that here I need to iterate through all the partitions. So computation of one of the value of one state is not something you can do easy in polynomial time. You still need an exponential number of partitions to do this. Yeah. So how do you? What will be the running time? Yes. So for every state, you will pay. So this is the sum over all subsets of terminals. Yes. And for a given subset of terminals, you will pay polynomial in n to for like ranging over all the use and easy computation in here. Yes. And you will browse through all the 2 to the size of x partitions. Yeah. So putting the poly n in the front, this is the sum over all subsets 2 to the size of x. Yes. And this, well, I can rewrite it as the sum over all from 0 up to the size of terminals, 2 to the I times the number of terminals. Choose I because this is the number of times particular 2 to the I happens here. And here you see 1 plus 2 to the power t, the Newton formula. So this is 3 to the t. You can, this is basic discrete math. So this is why this 3 to the t happens here. And actually, you can do what you can do. You can do 2 power the number of terminals, but only in the like a strong weakly polynomial setting. So here you've got polynomial in the largest weight. So you assume that the weights are integral and well, poly n. So you've got you are polynomial in the largest weight, and this is a result by Jesper Nadelov, and I think you can do some trade-offs. Between 2 and 3. I don't remember on the details, but I'm pretty convinced that we do not know a like strongly polynomial algorithm for running time 2 to the t for that. As far as I remember, maybe somebody can tell me if I'm wrong, but at least I don't. Good. So this was the Steiner tree problem. And this Dreyfus-Wagner algorithm, it appears a lot of times in many different settings in network design, mostly in, say, approximation schemes, where, for instance, you have carved your Steiner tree that you want to approximate into smaller pieces, and you know that in every piece you want to, say, connect 1 over epsilon terminals. Then you can run this algorithm in running time 2 to the power 1 over epsilon. This is a typical usage in combinatorial optimization. Good. I think that's it for today. So thanks a lot. And tomorrow we continue with tree width and with this kind of techniques, and in particular application of parameterized techniques on planar graphs and topologically restricted settings.